Okay, we were doing the proof of the following lemma here, and which got interrupted. So what we were doing is that we need to, so given a subset satisfying these three conditions, we need to show that for any distinct points, you can find a function which can take the desired values on the distinct points. So since A separates points by the separation property, there is a continuous function g such that gx and gy are distinct. So alpha not equal to beta. So let's just call gx to be alpha and gy to be beta. Now we are looking for a function f. So we are going to look for a function f in terms of g by choosing an appropriate s and t. So how do we choose this s and t such that it satisfies f of x to be a and f of y to be b, right? That's how you want so you want f to satisfy that, right? You want f to take the value a and at x and b at y. So f of x has to be a, which means s alpha, and at g of x the value is alpha, so s alpha plus t equal to a and s beta plus t equal to a. Here you can, since g is a known function, you can think of this as gy itself, right? So here s and t are unknown. Alpha a, beta b are known quantities, so you need to solve for s and t in the system of equation, this two system of equation, which you can actually do. So you can solve for s and t, you get s in terms of alpha, beta and a and b. Okay, so now note that sg plus t belongs to a. Okay, so note that that is how, because A is a subspace, so if it is just a dilation and a translation, so Sg plus T belongs to A, where because A is a linear subspace and the constant function 1 also belongs to A, right? That is the property that they are satisfying. So F belongs to A precisely, okay? So when A is equal to B, so what we are saying here is that in this theorem, it is not necessary that a and b, x and y are distinct. A and b can be chosen to be the same point. A equal to b can also be done. So we have found an f which takes, which is this f, which takes, and we have found this s for, so for this choice of s and t, we have an f which takes x to a and y to b. And when a is equal to b, you can check from these formulas that s is 0, t is a, so f is actually the constant function a, so it takes the value a at both x and y, in fact all points from the domain of f. So we have proved that result. Now let's look at the property when subsets become dense in the space of continuous function. So if X is a compact topological space and A is a subset of Cx satisfying the properties uh, here, right? Satisfying the properties here, this one. So A satisfies all these three properties, okay? And in addition, it also satisfies the lattice property, which basically means that if two functions belong to A, then the maximum of the two function also belongs to A and the minimum of the two function also belongs to A. That's what this notation means. So this this wedge notation basically means that maximum of f and g and minimum of f and g are also in A. So A is closed under maximum and minimum as well. If so, so those three conditions plus this lattice condition, if that is satisfied by a subset of a space of continuous function, then that set is dense in the space of continuous function under the uniform topology. Let's prove this here. So if f is a continuous function, what we need to, so you fix an f, what we need to show is that if A is dense, that means you can obtain an element G in A such that the distance between F and G can be made as small as you want. Right? That's what density of A in Cx means. So any given epsilon, we can get a G such that, and this norm is the uniform norm, that is supremum norm. So if you take any 2 points x and y which are distinct, then look at the value. Since f is the one that you have chosen, look what is f of x and call that a, and whatever is the value of f at y, call that b. So you have chosen two values a and b for the given f, right? Now x and y are distinct points. Now again, by the lemma that we proved above, there is a function gxy such that gxy at x takes the value a, which is fx, and gxy at y takes the value b, which is fy. Okay, this is from what we proved the previous thing. So two distinct points, it can take the value that you can prescribe. So you choose a function which takes the value fx and fy. So here if you notice, gxy minus f value evaluated at x is 0, gxy minus f evaluated at y is 0. So you define this function. So you fix x, now you only vary y. So for each fixed x, okay, and y, since x and y are distinct, you use the continuity of gx minus f, this function, gxy minus f, that function at y. So by the continuity of this function, right, by the continuity of this function, for any epsilon, you have an open set uxy contained in xy, so that within that open set, so for all elements of that open set, you have this inequality by the continuity of this gxy minus f, right? Okay, so this you can do for every y. So you actually have a collection of open sets indexed by y in x, okay, and they actually will form an open cover for x. Okay, so here I'm just rewriting here in the sense that whatever I have written here, in particular gxyz is less than fz plus 1. This is one part of this thing. This happens for all z in uxy. Now this is true for each y in x. So you take, for each y in x, you take you have a neighborhood, and all these open sets form an open cover for x, and by the compactness property here, by the compactness property of x, you have a finite subcover for this collection of uxy. So you actually have a finite collection uxy, so some yi points, such that the corresponding open sets actually is a cover for the given compact set. So the reason for doing this is, once we have this, we have a finite collection of open sets, which means we have a finite collection of yi's. So now you define your gx to be the minimum of gxy1 up to gxyn, right? Now by the lattice property of A, this gx belongs to A because each of this belongs to A. And you notice here that gxy satisfies this property for all z in uxy, which means gxy1 satisfies for uxy1 and so on. And all this uxyi will cover x. So you actually, and by the minimum property, this is valid for gx as well, because gx is smaller than this quantity for each yi that we have obtained. So gx of z also satisfies this property, but now for all z in x by the minimum property. So from this property, we have gxz less than fz epsilon for all z in x, right? And further you can verify that the value of gx at x is f of x. That is because the value of gxy1 at x for all these were f of x. Okay. Now for each fixed x, now you repeat the same argument for each fixed x. So from xy indices, we using compactness, we reduced by taking minimum, we have written the function as an indexed by x. Now this you can do for each x, whatever we have done. So for each x, you look at this function gx minus f at x, which is continuous at x, use the continuity property. You have an open set vx in x such that this happens. Okay, and in particular, you have gx bigger than fz minus epsilon for all z in vx. Repeat the same argument as above. Do this for every x. You have a do this for every x. You have a uh, open cover for this compact topological space. For the compactness, you can extract a subcover, so you have a finite collection x size, which such that Vx size will cover the topological space X. So now you will define G to be the maximum of all this GXM. So sorry, this should be GXM. Okay, so this should be GXM. Okay, now so which means that G is by the lattice property, G is also in A, right? And G is defined like this, and this G will satisfy this property that GZ is this. In fact, GXI was this, so GZ is greater than or equal to this for all Z in X. Now, combining from what we had before, we actually have that F minus G is less than epsilon for all Z in X, which is precisely what we wanted to prove. Okay, so we have actually shown the density of A. So this G was picked as an element of this A, right? That is how we have picked. Okay, so that kind of completes this proof. So if you have the fact, suppose there is a subset which is a subspace which contains the constant function 1 and hence all the constant functions, which separates points and is also a lattice, then that is a dense subset of the space of continuous functions. So this lattice set also has this property. You can verify lattice property of a subspace. Just that, I mean, so any subspace A is in the space. So in CX is lattice. If and only if so, it's a necessary and sufficient condition. But whenever F belongs to A, the mod of F also belongs to A, right? So it's a very simple proof. You can actually even do it as an exercise if you. It's a very simple exercise. So if A is a lattice and if F belongs to A, we need to show that mod F belongs to A. But mod F is precisely the maximum of F and minus F, right? Mod F can be written like that, and maximum of two functions in from A is in A by the lattice property. So mod F is in A. Conversely, if mod f belongs to A, so conversely, if mod f belongs to A, whenever f belongs to A, so we assume this condition, we need to show that A is a lattice. So we need to show maximum and minimum belongs to A. So you can see that maximum of any two functions can return in terms of this using the modulus of the function. So whenever f and g belongs to A, by the vector space property, f plus g belongs to A and f minus g belongs to A. By this property, if f minus g belongs to A, mod f minus g belongs to A, and the maximum is precisely sum of these continuous functions, which will be in A again. So it's a simple exercise that you can do. So you can check for the lattice property using this necessary and sufficient condition. Okay, now let's go to the Stone-Weierstrass theorem. So this is the real version of the Stone-Weierstrass theorem. When I say real version, what we mean is that the space of continuous functions here are actually real value. So if you have a subset of the space of continuous functions on a compact topological space X, and that A satisfies the property, the three property, that is vector space. It's a vector space, vector subspace. It contains the constant function 1. It separates points, right? And in addition, it satisfies the so the pointwise multiplication also. So it's closed under pointwise multiplication. Okay, this is like you can make this like an algebra. So So it's closed under pointwise multiplication. Then again, A is dense in the space of continuous function under the uniform topology. What is the proof of this? So you take the given A and look at its closure. Call it A closure, right? If we want to show that A is dense, we want to show that A closure is Cx. So we will actually show that A closure is the Cx, right? So you take A and denote A closure as the closure of A. A bar as a closure of A. So now this A bar also, so A closure also satisfies all the hypotheses of A. Okay. So by the previous theorem that we just showed, if we show that A bar is a lattice, then we can show that it is dense. That's what we showed in the previous theorem. So it's enough to show that A bar is a lattice, which means that it's enough to show that mod f belongs to A closure whenever f belongs to A closure. So if we show that, we have shown that A closure is a lattice, which means that A closure is dense, but A closure is already closed. So it has to be the entire Cx. So to do that, what we do is that we introduce this polynomial. So given any polynomial in x variable, you write down this polynomial form of any continuous function. Okay, so you have this function which is just pointwise product, right? Because pointwise product is assumed to be in A, so all this fn minus 1, all this will belong to A, and this dilation and sum of continuous functions. So this, so if you start with an f in A, this pf will also belong to A. Okay, so you start with this polynomial type function, continuous function. So if f belongs to A closure, pf also belongs to A closure by the all the property that we have that is given. Now by lemma 10, which is where we showed that we have a polynomials uniformly converging on compact sets to mod x, right? So here you see this is this we need to show mod f belongs to A bar, right? So f belongs to A bar, we have pf belongs to A bar, and we have this polynomials which converges to mod x, right? So you can think of f as composition with the mod function, the mod f as a function of composition, f composed with mod function. So you actually, so corresponding to these polynomials Pn, you actually have Pn f converging uniformly to mod f on x. Okay, and the uniform convergence on compact sets becomes uniform here because uh, mod f, the range of mod f is a compact subset of f, right? Because it's a continuous function on a compact set. So you have a collection sequence of continuous functions. Suppose so you start with f in a bar, and you have a collection of p and f, which is also in a bar, and it converges to mod f. Okay, which means that, and since a bar is closed, mod f has to be in a closure, right? So mod f belongs to a bar. Now now a bar satisfies all the hypotheses of the previous theorem, that is all the conditions plus the lattice condition as well. So a bar is dense in Cx. Okay, so that way a bar is a closure is Cx, which means A is dense in Cx. So this is the real version of the Stone-Weierstrass theorem, which gives you conditions under which a set can be dense in C of x. Okay, now let's, as a corollary, let's do this famous Weierstrass approximation theorem, right? So he was the first one who actually said that the class of all polynomials are dense in the space of continuous functions. So if you have a compact subset of the Euclidean space Rn, and if pk denote the space of all n variable, because we are in Rn, okay? So n variable real polynomials restricted to the compact set K, then this class of all polynomials in K is dense in the class of all continuous functions. That is every continuous. So this is C much more. For instance, so we started the lecture by actually showing that there is a sequence of polynomial uniformly converging to mod x. Mod x is a continuous function, and you can approximate it by polynomials. Weierstrass actually says that this can be done for every continuous function, not just mod x. Okay, so what is the proof? So uh, it's very easy to verify that this pk, that is a set of all polynomials, is a subspace, right? Addition, scalar multiplication, everything, it's closed under these operations, and it contains the constant polynomials, so it trivially satisfies those conditions. So, right, so any, if you know the multi-index notation, then any n variable polynomial can be written like this, right, where this x is now n variables, x1, x2 up to xn. Alpha is also an n tuple of integers, so these are powers of each component of the x depending on that, and mod alpha precisely means the sum of the components of alpha. So this is a very compact way of, so this is the multi-index notation. So this is the compact way of writing an n variable polynomial. Okay. So this px, so if we need to show this is dense in x by the real Stone-Weierstrass theorem, we just need to show that this pk satisfies all the conditions of the real Weierstrass theorem. So it's a subspace, it contains and it contains constant polynomials. It also separates points, right? Because if you take two points x and y such that they are distinct, then if they are distinct, which means that one of the coordinates is different, right? Because if all the coordinates are same, then they are the same point. So distinct vectors in Rn basically means at least one of the coordinate is distinct. So that's what this means. Is there is an I such that this happens for some I. Now you consider this polynomial, which is the projection to the uh, ith real line, right, ith axis. So which is x projected to xi component for the chosen I for which this is distinct. Now this separates points, and this is a continuous function. Okay, so this pk is also a set which also separates points. So it's dense in ck. Okay. uh, did we check everything? Wait a second, just a second. Yeah, we need to, yeah, product of polynomials. uh, Product of two polynomial is also a polynomial, right? We need to, I forgot to probably mention that. So that is also true. So we have the density of the class of all polynomials in the space of all functions. Okay. Okay, now let's try to do the complex Stone-Weierstrass theorem. So the complex Stone-Weierstrass theorem is the same as the one previous before, but just that now you have an additional property. So first you are having continuous functions which are complex valued, and A is a subset of that. So satisfy the properties as in theorem 26 basically means all those properties, that is subspace, constant functions are contained, separates points, and then in addition you had the algebraic, that is pointwise product. It's a kind of closed under pointwise product. And now in addition to that you have a fifth condition, which is that the conjugate, because it's a complex function, the conjugate of any function, so it's also closed under conjugation. The set is closed under, the set A is closed under conjugation. So if these conditions are satisfied, these 5 conditions satisfied, then A is dense in the continuous functions of all the complex valued continuous functions on X. So the proof is um, also quite simple. So what you do is that you are given an A, you look at all the real valued subclass of the given subset A. Okay, so A0 is contained in A. right? So, but A0 is all real valued functions on X. Now, since A is closed under the conjugation, if you take any f in A, the real part of f and imaginary part of f is belongs to A0, right? Because both real part of f and the imaginary part of f can be written in terms of f and f bar, right? Real part of f is f plus f bar over 2, and imaginary part of f is f minus f bar over 2y, and so on. So, and they are all subspaces, so this is it's uh, it's valid. And then so real part of f, imaginary part of f belongs to A0. Okay. So we now verify that, we now claim that this A0 that we have obtained satisfies the hypothesis of the real Stone-Weierstrass theorem, because now they are all real valued functions. Okay. So everything, so subspace will be satisfied, constant functions are satisfied because they are real valued functions. So separate points is what we need to check, right? In fact, the algebraic condition, the pointwise product will also be satisfied, closure under pointwise product. So separating points, a separating point is also easy to check, that since A separates points, there is a function f which will separate, say, 0, and which will take the value 0 at x and 1 at y. Okay, so you can find an f like that. Now what you do is that you look at the real part of f, real part, because the values are real, 0 and 1. The real part of f will also do the same thing. Real part of f is 0, real part of f at y is 1. So real part of f which belongs to A0 separates these two distinct points x and y. So A0 satisfies all the conditions of all the hypotheses of the real Stone-Weierstrass theorem. So A0 is dense in the space of all continuous functions, right? So if f is a complex valued function, and then the real part of f and imaginary part of f belongs to the real valued continuous functions, right? And A0 is dense in the real valued continuous functions. So which means that the real part of f and imaginary part of f can be approximated by real valued polynomials from A0, right? Which basically means, so f can be written as real part of f plus I times imaginary part of f. Both these can be approximated by functions from polynomials from A0, which means that f can also be approximated by polynomials which are complex valued, right? Which means that A is A is dense in Cx, because A is precisely uh, wait a second. Yeah, so I have taken an f, I have found real part of imaginary part of f. Whatever approximation that I do here, if I sum them, that will belong to A, right? So that is how A is dense. Okay. Yeah, fine. Now let's do finally the separability of the space of continuous functions. So this is a corollary of the Weierstrass theorems, Stone-Weierstrass theorems, is that uh, if X is a compact metric space, then the space of all continuous functions on X is separable. In particular, when X is the interval, this is true, right? Okay, so how do we prove this? That is a separable. So what is separable? Separability means, that means there is a countable dense subset. So in the space of all continuous functions, you need to find a countable dense subset, right? Like in the space of R, so rationals is a countable dense subset. So R is separable. So here in the space of continuous functions, we are claiming that so this is separable. So we need to find a countable dense subset. So you start with uh, an f in CAB. Okay, so I'm giving the proof here for the CAB. So you start with an f in CAB. Then there is a polynomial right? There is a by the Weierstrass theorem, there is a polynomial such that uh, you can make it as close to f as you want, right? So you can choose a polynomial p such that under the uniform metric this happens. Okay, now since rationals are dense in R, this Ck, which are the coefficients, can be approximated by rationals. So every real number can be approximated by a rational. So corresponding to Ck, we choose a rational such that this happens. Okay, it is smaller than, I mean, it is, the distance between them is smaller than this quantity. So now you define this new set of polynomials Q where the coefficients Ck's are replaced by this nearest rationals that we have, closest rationals, that, not closest, the, I mean, the rational that we chose near Ck. So you define those polynomial. Then the distance between these functions, these polynomials P and Q, is this, right? This can be chosen because this is supremum norm. So this is and this is how we chose Ck minus Rk. So this is precisely epsilon over 2. Okay, which is why we chose this n plus 1 here. So these two polynomials differ only by epsilon over 2. F minus p differ by epsilon minus 2, which means f minus q differ over epsilon. Now q is a polynomial with rational coefficients. So what we have shown here is that polynomials with rational coefficients are dense. Now, only thing that we need to show is that polynomials with rational coefficients are countable. Okay, that I leave it as an exercise for you. It's an easy thing to do, right? So you have a polynomial here, which means you have rationals here. Now, uh, you have finite numbers because there are, I mean, it's a polynomial of degree n, so you have finite number of rationals here, and the possibilities for these rationals are countable. It's like finite union of countable collection, right? So you can very easily verify that the rational coefficient polynomials are countable. So you actually have obtained a countable dense subset of CAB. So CAB is separable. This you should be able to generalize to Euclidean space as well, right? So I've given it for the interval AB. Okay, so with this we stop here. Now that we have talked about dense sets, maybe in the next lecture we have approximated by polynomials here. In the next lecture we will talk about using the Weierstrass theorem. We'll talk about approximation uh, by the trigonometric polynomials and so on. Okay, thanks a lot.